There's a number that the city of New York kept secret for 17 years. That number is 16, as in 1 chance in 16. As in, every single year that a 59-story skyscraper stood open for business in the middle of Midtown Manhattan, the probability that it would fall down and kill everyone within a 10-block radius was 1 in 16. Not 1 in 1,000, not 1 in 100, 1 in 16, every year. That building had 50,000 occupants on a working day. It sat at one of the busiest intersections in the most densely populated urban grid in the Western Hemisphere. It had been open for 11 months when an engineer discovered the flaw. The engineer was the same man who designed the building. He sat with that number, 1 in 16, alone in his office in Cambridge, Massachusetts, for days. He considered 3 options. He later described them himself in a Harvard lecture after the secret was no longer a secret. Silence, suicide, confession. He chose confession. And then, within weeks of that confession, everyone who learned the truth agreed to keep it from the 50,000 people inside the building. From the mayor of New York, from the city's buildings department, from every commuter who walked through that lobby every morning without knowing that the walls around them had been opened at night and welded shut before dawn. The secret held for 17 years. The number was 1 in 16. That is the beginning. This is the rest of the story. Here is what William Le Mesurier's Harvard lectures did not explain. Le Mesurier taught engineering ethics at Harvard for years after 1978. He used the Citicorp story as his primary case study. He described it as a lesson in professional courage. The engineer who found the flaw in his own building came forward and made it right. The engineering community praised him. His reputation, which he had feared the confession would destroy, was instead elevated. Structural engineers across the country taught the case in classrooms, citing it as the model of how the profession should behave when something goes wrong. There was just one problem. The version Le Mesurier told at Harvard was not the complete version. The complete version, including the deliberate decisions about who was informed in what order, with what instructions about public disclosure, and what was placed in a private file labeled Project Serene, was not published until attorney and historian Michael M. Greenberg dug into Le Mesurier's own documents and released his findings in a book called The Great Miscalculation, published by NYU Press in 2025. The case study that an entire profession used to teach honesty was itself incomplete. The story of the cover-up had its own cover, and both covers, the original secrecy of 1978 and the incomplete telling of 1995, protected the same thing. The fact that 50,000 people went to work every day in a building with a 1 in 16 annual probability of collapse. And not one of them was told. This is the full story. Start in 1973, Lexington Avenue and 53rd Street, Manhattan. A Lutheran church called St. Peter's occupies one corner of a midtown city block. The rest of the block belongs to Citicorp, one of the largest banks in the world. Citicorp wants to build a skyscraper. St. Peter's wants to stay. The negotiation is brief. St. Peter's agrees to sell its corner on one condition. Citicorp must build the church a new home on the same site. And the corner of the lot, the exact ground beneath where the church stands, must not be touched by the skyscraper above it. That condition changes everything. The architect is Hugh Stubbins. The structural engineer is William J. Le Mesurier, a professor at Harvard, a nationally honored innovator, a man whose firm has designed some of the most technically sophisticated structures in the country. Le Mesurier's challenge is not aesthetic, it is physical. Skyscrapers transfer their weight to the ground through columns. Those columns live at the corners. Corners are where the structural loads concentrate. Corners are where a building is strongest. Building a skyscraper without using one corner of its footprint is not a design constraint. It is a structural paradox. Le Mesurier sketches a solution on a napkin at a Greek restaurant on Lexington Avenue. He will move the columns, not to the corners, to the centers. 4 massive stilts, one at the midpoint of each of the building's 4 sides, carry the entire tower 9 stories above the street on a structural deck. The building's corners hang free in the air. The new St. Peter's Church sits in the shadow of one of them, untouched. To handle wind loads on a building with no corner columns, Le Mesurier designs a chevron bracing system. Large, diagonal V-shaped steel braces stacked in tiers through the full height of the tower, channeling wind forces from the upper floors down to the 4 midpoint stilts. It is brilliant. It is unconventional. And it works, provided the chevron joints transfer load the way Le Mesurier specified. He specifies welded joints. Welding creates a continuous metallic bond across the full surface of the connection. It is structurally the most reliable option for a joint carrying this type of load. Construction begins in 1974. Standard practice in many applications. The substitution saves $250,000. Designs for the bolted joints are produced based on load values supplied by Le Mesurier's own Cambridge office. The change is made. Le Mesurier later says he was not consulted. A member of the joint venture engineering team later says he was. The discrepancy is never resolved. What is not in dispute is the outcome. On October 29, 1977, Citicorp Center opens. The 59-story tower with its distinctive slash-topped crown and its silver glass exterior becomes an immediate landmark. Architecture critics call it transformative. Structural engineers cite the midpoint stilts and the chevron bracing as a breakthrough. The tuned mass damper installed at the top, a 400-ton concrete block on a frictionless oil film connected to pneumatic springs, calibrated to swing 90 degrees out of phase with the building's natural oscillation period of 7 seconds, is the first active mechanical stabilization system ever installed in a skyscraper anywhere in the world. Le Mesurier is celebrated. 50,000 people begin arriving every morning. Here's what the building's opening day does not explain. In May 1978, Le Mesurier is working on a different project in Pittsburgh. He wants to use a similar chevron bracing system on the new building. A contractor questions the cost of welded joints. Le Mesurier calls his New York office and asks how the Citicorp welding went. He is told they used bolts, not welds. He makes a note and moves on. The next month, June 1978, a phone call arrives at his Cambridge office. The caller is a young man from New Jersey, a freshman architecture student at the New Jersey Institute of Technology named Lee DeCarolis. His professor has assigned the class to write about a building of unusual structural design. DeCarolis has chosen the Citicorp Tower. He calls the structural engineer directly. They talk for 30 minutes. DeCarolis asks about the midpoint columns. He mentions that his professor thinks the columns look like they are in the wrong place. Le Mesurier is not alarmed. The call ends. At approximately the same time at Princeton University, a senior architecture student named Diane Hartley is writing her undergraduate thesis. Her subject is also Citicorp Center. Her advisor is David Billington, one of the most respected structural engineering educators in the country. Hartley's thesis is about the relationship between architectural form and structural system, how the visible shape of a building reflects or contradicts the forces that hold it up. She calls Le Mesurier's firm. She speaks not to Le Mesurier, but to a junior staff member named Joel Weinstein. She asks a precise question. The building code, she knows, requires wind-load analysis for perpendicular winds that strike the flat face of a building directly. But this building is not a conventional building. Its columns are at the midpoints, not the corners. What happens, Hartley asks, when the wind hits the building at 45 degrees? When it strikes the corner instead of the face? When it approaches from the angle that engineers call a quartering wind? Weinstein provides her with the firm's calculations for perpendicular winds. He does not provide calculations for quartering winds. She asks for them. He says he will send them. He does not send them. Hartley finishes her thesis and submits it. She does not know what her question is planted. On July 24th, 1978, Le Mesurier sits at his desk. The two phone calls, DeCarolis and the question about column placement, Hartley's inquiry, and the missing quartering wind calculations have been circling in his mind. He runs the numbers. He calculates what happens to the Citicorp Tower's chevron braces when a storm strikes the building from a quartering direction. At 45 degrees, aimed at the corners between the midpoint stilts. The calculation takes hours. The answer arrives in stages. First number, quartering winds increase the load on the chevron braces by 40%. Second number, the 40% load increase translates to a 160% increase in stress at the bolted joints, because the bolt carries the load through a single point of mechanical contact, rather than the continuous metallic bond a weld provides. Third number, at that stress level, 4 of the 8 tiers of chevrons are vulnerable to failure. Fourth number, Le Mesurier cross-references the structural failure threshold with 70 years of New York City wind data. The storm capable of generating the quartering wind load that triggers failure strikes New York City on average once every 16 years, 1 in 16 per year. He then calculates a second scenario. The tuned mass damper at the top of the building runs on electricity. In a storm severe enough to approach the structural failure threshold, power outages are likely. Without electricity, the damper stops. Without the damper, the building's effective resistance drops further. Without the damper, a storm capable of toppling the building hits New York not every 16 years, but more frequently. Le Mesurier maps the collapse zone. 59 stories, 53rd Street and Lexington Avenue, the heart of Midtown Manhattan. A falling tower does not stay within its own footprint. It transfers energy outward. Surrounding structures absorb that energy. Radius of primary destruction from a progressive collapse at this location. 10 city blocks. Population within that radius on a working weekday, approximately 200,000 people. Le Mesurier closes the file. He sits with what he has found. He is 51 years old. His firm is one of the most respected structural engineering practices in the country. His name is on this building. His calculations are in its foundation documents. And the building is killing everyone inside it at a rate of 1 in 16 per year. Stop here. Because what quartering winds do to a building with midpoint columns is the part that no inspection, no code review, and no certification process in 1978 was designed to catch. Here is what the New York City Building Code of 1970 actually required. Wind load analysis, perpendicular wind load analysis. The code specified that structural engineers must calculate the force exerted by winds striking the face of a building directly at 90 degrees to the surface. This requirement exists because in the overwhelming majority of building designs, perpendicular winds produce the worst structural case. When a wind hits a building face on, the full projected area of that face resists the load. The columns at the corners absorb the force directly. The structure is at maximum efficiency. Quartering winds, diagonal winds at 45 degrees to the face, are typically less severe than perpendicular winds in buildings with corner columns. The corner column sits exactly where the diagonal load wants to go. The structure handles it without additional analysis. The code does not require quartering wind calculations because in standard building design, they are unnecessary. The Citicorp Tower is not a standard building. TS columns are not at the corners. They are at the midpoints. When a quartering wind strikes the Citicorp Tower at 45 degrees, it hits the building at the point furthest from any column, the hanging corner between two midpoint stilts. The load travels diagonally inward, seeking the nearest structural path, arriving at the chevron braces at an angle they were not fully analyzed to resist. Now add the bolted joints. A welded joint creates a continuous metallic bond across the entire contact surface. Load spreads evenly across the weld. The structural calculation for a welded joint accounts for that distribution. A bolted joint concentrates the load at the bolt itself, a single fastener point rather than a distributed surface. The engineering formula for a bolted joint under shear load includes a leverage factor, a multiplier that reflects how much the eccentric load path increases the force at the mechanical fastener. When Le Mesurier ran the quartering wind case through the bolted joint formula rather than the welded joint formula, the 40% load increase became a 160% stress increase at the fastener. Not because the bolts were installed incorrectly, not because the bolts were substandard, because the design loads used to specify the bolts were calculated for perpendicular winds, which the code required, rather than quartering winds, which the code did not require and which the unique geometry of this specific building made the actual worst case. The code was followed, the calculations were performed, the joints were installed to the loads specified, and the result was a building with an annual collapse probability of 1 in 16 that passed every certification the system required. No individual made a reckless decision. The system produced a dangerous building by doing exactly what it was designed to do. That is not a reassuring conclusion. It is the most unsettling one possible. Because it means the gap was not in someone's negligence. It was in the code itself. And the code did not change until after the secret had already been kept for years. Le Mesurier contacts Hugh Stubbins, the architect. He contacts his professional liability insurer, Northbrook Insurance. He contacts Citicorp's senior leadership. He walks into a room with Walter Wriston, the chief executive of Citicorp, one of the most powerful financial figures in the United States, and tells him the truth. Wriston does not panic. He asks what it will take to fix it. Le Mesurier has an answer ready. 2-inch steel plates welded over every one of the 200 bolted joints in the chevron brace system. The plates restore the load transfer capacity the welded joints would have provided. Installed correctly, they transform a building vulnerable to a 16-year storm into a building capable of withstanding a 700-year storm. The structural math is clean. The logistical problem is everything else. The building has 50,000 occupants. The joints are embedded inside finished interior walls. Accessing them requires removing wall panels. Welding requires open flame and grinding equipment. Grinding and welding inside an occupied office building during business hours is not possible. The decision is made. The repairs happen at night. Every evening, after the last occupant leaves, a team of welders enters through a service entrance. They remove the interior panels section by section. They grind the surfaces. They apply the 2-inch plates. They weld them into position. They reinstall the panels. They are gone before the first commuters arrive. During the day, the freshly repaired walls look untouched. The 50,000 people arriving each morning walk past walls that were opened 4 hours earlier. They notice nothing. They are told nothing. The mayor of New York City, Ed Koch, is informed. The acting buildings commissioner, Irving Minkin, is informed. The head of the welders union is informed. The police department works with the repair team to prepare an emergency evacuation plan covering a 10-block radius. That plan exists on paper. It names 200,000 people. It sits in a file. Nobody in that 10-block radius is told it exists. Northbrook Insurance dispatches its legal team and backs the repair financially. Their guidance is specific. Public disclosure risks mass panic. The confidentiality is maintained. The welders work. The plates go on. August becomes September. On the morning of September 1st, 1978, every weather service that Le Mesurier has hired, 3 of them providing reports 3 times a day, delivers the same forecast. Hurricane Ella, off Cape Hatteras, moving northeast toward New York City. The repairs are not finished. The most critical joints and the most vulnerable tiers have been addressed. The remaining joints have not. The building is better than it was in July. It is not yet what it needs to be. If Ella makes landfall anywhere near Manhattan with the winds it is carrying off the Carolina coast, the partially repaired building faces a storm in the range of its remaining vulnerability. The evacuation plan is reviewed. Officials with knowledge of the situation, a group small enough to fit in one room, discuss whether to activate it. 200,000 people, 10 blocks, overnight. In a city whose major newspapers, the Times, the Daily News, the Post, are all on strike. The irony is exact and total. The single moment in the post-war history of New York City when the print press cannot cover a story about the city's most dangerous building is the same moment the most dangerous thing that could happen to that building is approaching from the Atlantic. Le Mesurier later says, "We were sweating blood." Before dawn on September 2nd, 1978, Hurricane Ella turns. It veers northeast. It accelerates away from the American coast. It intensifies over the open Atlantic and strikes Canada with winds of 225 kilometers per hour. Not Manhattan. Not the half-repaired chevron joints on the floors where the welders have not yet reached. Not the 200,000 people in the 10-block evacuation plan that nobody outside the conference room knew existed. The next morning, Le Mesurier describes it as the most beautiful day the world has ever seen. The welders go back in that night, and the next, and every night through October. The final plate is welded in October 1978. The building that could withstand a storm occurring once every 16 years can now withstand a storm occurring once every 700 years. The repair costs between $4 and $12 million, depending on the accounting methodology. Northbrook Insurance contributes $2 million. Citicorp agrees not to pursue legal action against Le Mesurier. The file labeled Project Serene is closed. And the secret, the number, the probability, the overnight welders, the hurricane, the 10-block evacuation plan is sealed inside a private archive for 17 years. Here is what the 1995 New Yorker article does not explain. In 1993, Le Mesurier is at a dinner party. He tells the story, not the sanitized Harvard ethics lecture version, but the full story, with the hurricane and the sweating blood and the evacuation plan and the newspapers on strike. A film critic named Joe Morgenstern is listening. Morgenstern has never written about engineering. He has never covered a construction story in his career, but he recognizes what he is hearing. He spends 2 years reporting it. On May 29, 1995, The New Yorker publishes The 59-Story Crisis. The engineering world reads it overnight. By the following semester, it is in every structural engineering ethics curriculum in the United States. The narrative that emerges from the 1995 article is one of professional heroism. An engineer discovers his own mistake. He comes forward. He fixes it at personal risk. He emerges with his reputation intact. Enhanced, even. The moral is clear. Honesty, even painful honesty, is the right choice. That narrative is not false, but it is not complete. In 2025, Michael M. Greenberg publishes The Great Miscalculation through NYU Press. He has spent years with Le Mesurier's private files, including the Project Serene documentation that did not appear in Morgenstern's article. What Greenberg finds is more complicated than the ethics lecture version. Le Mesurier's role in shaping the public narrative, in deciding what to disclose, to whom, in what form, and with what legal scaffolding around it, was more deliberate than the 1995 account suggested. The decision to keep the repairs secret from the building's occupants was not simply a practical choice made under time pressure. It was a coordinated decision involving lawyers, insurers, city officials, and Citicorp's leadership. A decision that prioritized the management of information as carefully as the management of the structural failure itself. The 50,000 people inside the building were not informed because the people who knew decided they should not be. Not because there was no time, not because there was no mechanism. Because the assessment was made by the people in the room with the file labeled Project Serene on the table, that the occupants of the building did not need to know that the building they were in had a 1 in 16 annual probability of killing them. Greenberg's book is reviewed in Engineering News Record in April 2025. The review notes that the narrative produced by the 1995 article, the one that became the foundational ethics case, was itself shaped by Le Mesurier's account of his own behavior. And Le Mesurier, it turns out, had strong reasons to shape it carefully. He was, after all, the man who designed the building. Both things are true about the Citicorp Tower. By any measure of structural engineering innovation, it is one of the most significant buildings constructed in New York in the 20th century. 4 midpoint stilts carrying a 59-story tower 9 stories above a Lutheran church that could not be moved. A chevron bracing system that had never been attempted at this scale. The world's first tuned mass damper installed in an occupied skyscraper. A 400-ton concrete block calibrated to swing against the building's own oscillation period of 7 seconds, saving an estimated $4 million in additional structural bracing. A building that transformed what midpoint column design could accomplish in a dense urban environment with irregular site conditions. A landmark so immediately recognizable that its slash-topped silver silhouette became part of the New York skyline within months of its opening. And it is also a building that had a 1 in 16 annual probability of collapsing onto 200,000 people for every year it stood without repairs. A building whose critical structural joints were changed from welded to bolted during construction, saving $250,000 on a project worth hundreds of millions, without a full recalculation of the change joint behavior under the wind direction. The building's unique geometry made its actual worst case. A building whose flaw was found not by the certification process that approved it, not by the inspection regime that issued its certificate of occupancy, not by any of the engineers or officials whose professional function was to catch exactly this kind of error, but by a junior architecture student whose question went unanswered and a senior engineer who finally ran the numbers himself. A building whose overnight repair operation was conducted behind interior wall panels, while 50,000 occupants worked inside it by day, whose emergency evacuation plan covering 200,000 people was prepared in secret and never activated, only because a hurricane turned at the last possible hour, and whose full story was not told until 27 years after the repairs were complete and 17 years after the first public account appeared. A building that became the foundational ethics case study of an entire profession, based on an account that was itself incomplete. The repair was real. The building is safe. It has been safe since October 1978, safer, in fact, than almost any building of its era. But the 50,000 people who walk through the lobby every morning between August and October 1978 did not know what was happening in their walls at night. The 200,000 people in the 10-block evacuation plan did not know their names were on it. The city did not know. The press did not know. And for 17 years, everyone who did know agreed. In a room, with lawyers present, with a file on the table labeled Special Engineering Review of Events Nobody Envisioned, that nobody else needed to. The number was 1 in 16. The secret lasted longer than the risk did. And the building is still there. 601 Lexington Avenue, the slash-topped silver tower on the corner where a small church refused to move. The chevron braces are welded now. The 2-inch plates are behind the walls. The risk is gone. The question that the 1 in 16 probability leaves behind, about who gets to decide what the people inside a building are told about the building they are inside, does not have a welded answer. It is still open.